Hello everyone, my name is Franklin.
And I'm Adinda Salsabila Sarina.
Today we are going to discuss about soluble substance distribution between two immiscible solvents. This experiment aims to determine the distribution coefficient K and degree of dissolution N of acetic acid distributed between two immiscible solvents, water and ether, using liquid-liquid extraction and acid-base titration. Standardization of NaOH, which is sodium hydroxide, using oxalic acid yielded a normality of 0.212 normality, which was then used to titrate acetic acid solutions after extraction to determine their concentration in the aqueous phase, while the organic phase concentration was calculated indirectly by subtracting from the initial concentration. A plot of log C organic versus log C water produced a linear regression equation such as log C organic equals 1.87 times log C water plus 0.513 with an R squared value of 0.96. This results in K equals 0.574 and N equals to 1.87. The result indicates that acetic acid is more soluble in ether than in water due to intermolecular association such as hydrogen bonding in the organic phase, while deviations in the degree of dissociation from the theoretical value and approximately equal to 2 may be attributed to experimental errors and additional interaction between solute and solvents.
And the next integration, the distribution of solids between two immiscible solvents is a fundamental concept in physical chemistry with broad application in fields such as mathematical, analytical chemistry, and chemical engineering. This experiment focuses on the distribution of acetic acid or with organic acid between water and aqueous solvent and ether and organic solvent, two immiscible pairs based on the Nernst distribution law. And the next discussion, first of all, a standardization of NaOH solution with 0.2 normality oxalic acid solution. First of all, measure 10 ml of 0.2 normality oxalic acid solution and transfer it into an Erlenmeyer flask. Oxalic acid is used as a primary standard because its concentration is accurately known. By transferring a precise volume 10 ml of the solution into an Erlenmeyer flask, we ensure that the amount of oxalic acid available for titration is consistent and reproducible. And then 2. Titrate the oxalic acid solution with the NaOH solution and record the volume of NaOH used during the titration. Titration is performed to determine the exact concentration of the NaOH solution since NaOH is hygroscopic and can absorb moisture from the air. This concentration may change over time. By titrating again a known concentration of oxalic acid, we can standardize the NaOH solution to obtain its precise concentration. Repeating the titration 3 times ensure accuracy and minimize random error. And then 3. Repeat step 1 and 2 3 times to obtain accurate result. And 4. Determine the exact concentration of the NaOH solution based on the titration data. The average volume of NaOH used in the titration is calculated, and this value is then used to determine the molarity of the NaOH solution. This standardized NaOH solution will be used later to titrate the aqueous phase of acetic acid after extraction, ensuring accurate measurement of acetic acid concentration, and result from data, normality annum here is 0.2 to normality.
Okay, next we will determining the distribution of acetic acid in two immiscible solvents. First, prepare acetic acid solution with concentration of 0.04, 0.08, 0.12, 0.16 and 0.2 normality. Preparing a series of acetic acid solution with varying concentration allow us to study how the distribution of acetic acid changes with different initial concentrations. This variation helps establish a relationship between the concentration in aqueous and organic phases. Second, take 15 ml of each prepared acetic acid solution and transfer it to a separative funnel. A separative funnel is used because it facilitating the mixing and separation of two immiscible liquids. By adding the acetic acid solution to the funnel, we can easily combine them with the organic solvents, ether or tetrachloride, and allow equilibrium to be reached. Shake thoroughly until equilibrium is reached, then allow the phases to separate, water and ether. Separate the aqueous layer and titrate it with 0.2 normality of NaOH. Calculate the concentration of acetic acid in the solution. Next, we will show you our calculation formula. Then, we will determine and create a plot between log C organic as the y-axis and log C water as the x-axis. Hydrogen bonding plays a significant role. In water, acetic acid forms hydrogen bonds with H2O, enhancing solubility. In ether, acetic acid associates into dimers, reducing effective solute concentration. These phenomena affect the measured values of K and N, highlighting the importance of molecular interaction in determining solute behavior.
This experiment demonstrates the practical application of the Nernst distribution law and highlights the importance of understanding molecular interaction such as hydrogen bonding, association, and dissociation in determining solute behavior in different solvent environments. The obtained value of K 0.574 and N 1.87 reflect the dual nature of acetic acid in polar and non-polar media. Despite minor deviation, the results are consistent with theoretical expansion and provide valuable insight into liquid-liquid interaction.